Hello. In this presentation, I'll be talking about the reaction of osmium carbyne complexes with bromine. First, I would like to introduce my starting complex. So in the top left, you'll see a 16 electron octahedral osmium carbyne complex where the osmium is in a +3 oxidation state. The carbyne bond itself represents a single instance of sigma donation from the carbon to the metal and two instances of pi donation from the metal to the carbon. As for the other ligands, chlorine atoms are pi donors, and the triarylphosphine ligands are pi acceptors, as well as sigma donors. Usually, carbyne complexes will react through the metal center via a redox reaction. For example, in the light green box here, the reaction shown is an oxidative addition reaction which turns the triple bond to a double bond and places a charge on the osmium metal. However, if we look at our reaction, which is just above it, there is no addition reaction. Instead, a series of ligand substitution reactions occur. You might be thinking, hang on, the starting complex is 16 electron complex, and it clearly has an open coordination site, so why does an addition reaction not occur to satisfy the 18 electron rule? And this is something I will touch on after looking at the mechanism. So let's have a look at the mechanism. It's a very simple mechanism and occurs in 4 steps. Firstly, bromine dissociates in wet DCM in a 1:20 molar ratio. A bromide ion will then enter a vacant coordination site and form a partial bond with the metal while weakening a metal ligand bond. A ligand such as chlorine will then leave the coordination sphere and the ligand substitution will be successful. This will repeat twice more with bromine and once with water while keeping the triple bond intact. A very important thing to note is that the water ligand has only ever really been observed trans to the triple bond, which is quite uncharacteristic as other similar reactions will have it trans to something like the phosphine ligand, for example. Finally, I would like to have a look at the structure of the product complex. The main thing that jumps out is that it is pretty much identical in geometry and structure to the starting complex, as the only thing that occurred is ligand substitution, which did not change the geometry of the complex. The oxidation state of the metal has also not changed, and the triple bond is still intact. The main interest of this product lies in the water ligand. Using X-ray diffraction, the water molecule has been observed to always be trans to the triple bond, even though two other isomers are plausible in theory. The 3 isomers can be seen here as A, B, and C, where A is the one that is majorly observed. To understand why it is only observed in one position, computational techniques like quantum calculations were performed. These calculations compared the bond lengths, angles, and relative stabilities of isomers A through C, and what was found is that isomer A is by far the most stable, with isomer C in fact being the most unstable. Now this is believed to be due to the trans influence of the surrounding ligands, namely the triple bond. The triple bond is a great sigma donor, and so it has a strong trans effect. This lengthens the bond between the metal and the water ligand. However, because this bond is much stronger than the metal-bromine bond, this arrangement of ligands is most thermodynamically favorable, and so is always observed. This thermodynamic stability is also the reason for the ligand substitution occurring over an addition reaction, which would satisfy the 18 electron rule, which is still theorized, however not really observed in this context.